Before you watch this video, I will recommend you to watch the videos called interference and thin film interference. When a curved glass surface is placed in contact with a flat glass surface, a series of concentric rings like in this picture is seen when illuminated from above by either a white light, in this case we have a white light, or by monochromatic light. These two green and yellow pictures are photographs taken from the Newton's rings under the microscope, traveling microscope. Now let's try to understand the physics of observed interference in these Newton's rings. For that, let's draw the arrangement of a flat glass and a plano convex lens on the top of this flat glass. So if we shine a light from top on this arrangement, we will observe Newton's rings that look like this. These rings are due to the interference between the waves reflected by the top and the bottom surfaces of the very thin air gap between the two pieces of glass. So here we have an air and air. So a little exaggerated picture is when we have a light ray incident and then it transmits through the glass and then again through the air. Actually, my drawing is a little bit off, so it should come a little bit. Let's start all over. I need normal. So here's the incident ray, and it's gonna refract inside, and then it's gonna refract again outside. Okay, so one is going to be reflected from this surface. Okay, another one is going to reflect from this surface. So these two waves, 1 and 2, are going to interfere and make destructive or constructive, interfere constructively or destructively and create rings. Because the thickness starting from the contact point is constantly changing, then you will have multiple rings created. Let's consider a dark fringe with the radius r at a point P, let's say right here. And suppose that the lens curved surface has a radius r, so therefore this one is also an r. And then I can say that our dark fringe will have a radius of little r. I'm going to call this one r, where the thickness is thickness of the air would be this pink part, and let's call it T. Now this part that I am going to mark with green will be R minus T, because this much from here to here, let's name it here Q, a point Q, OQ is T. And let's call the center of the curvature to be C. If we take a look at the triangle C, Q, and P, then Pythagorean theorem gives us r squared equals little r squared plus r big R minus t squared. Let's simplify this a little bit. R squared equals r squared plus r squared minus 2rt plus t squared. The big R squared squares will cancel out, and we will end up having 2rt equals r squared plus t squared. Well, yes, I think you noticed as well that I made a little bit mistake in here. This has to be a capital R, and so this one has to be capital R. So let me rewrite it nicer. So I have a 2rt equals r squared plus t squared. So here our t is several wavelengths or something like that, while the ring radius, little r, is usually some millimeters. So because t is way less than r, we can neglect t squared. So I can rewrite my equation as 2rt equals little r squared. Now for a dark fringe, we know that 2nt equals m lambda. Check the video on thin film interference if you are not sure where this is coming from, where m equals 0, 1, 2, and so on. Now I can find the t from here. That equals m lambda over 2n, and plug in this expression for t in my equation. This will give me the radius of the dark fringe squared equals 2 times the radius of the surface of the lens times m lambda over 2n. So the 2's will cancel out, and we will end up having r squared equals r big R m lambda over n, or if we want to find the radius of any dark range, mth dark range, that is a square root of r m lambda over n. Thanks for watching. Stay tuned for more.